So welcome to the final lecture on the proof complexity as a computational lens course, which is going to be mostly a non-technical lecture, I think. Almost no proofs, but hopefully lots of discussions. Maybe some formal argument towards the end if we still have the energy, but and let's see if we can get the slides to move. So yes, okay. See if I can learn the pointer. Okay. Except not. What are we supposed to do? I'll talk a bit about what we covered in this course, just this kind of recap and try to put it in context, like why did we select these results? How do they fit together? And then there was something that we would have liked to cover, but didn't quite get there. We'll talk about stabbing planes, Shirley-Adams squares, resolution over parities, and then also have a discussion of some things that we absolutely did not cover, but giving such a long course on proof complexity and not even talking about it would be a little bit weird. So that's like the final third of the course. Of the lecture, sorry. And I should say, as always, the slides, I mean, the lecture has been prepared maybe with not ideal forward notice. In this particular cases, I wanted to do this with slides. This means that there should be lots of nice references. They're just not there. So like, let me issue a blanket apology for this. I think I was pretty careful in earlier lectures, and Kilian also with giving the appropriate references. They will not be there today. So, but if you go back to the references to the lectures where we covered these results, I think everything should be there, hopefully. I mentioned it in general. I think, although it has a proof complexity and SAT solving focus, the proof complexity chapter in the SAT handbook is probably still a pretty good modern, like the most up-to-date reference for what we're covering. Of course, Krajicek's book is much more comprehensive and has also more coverage of the advanced topics. But I think one thing that maybe both the survey chapter by myself as Sambas and maybe also to some extent Krajicek's book is missing out on is the semi-algebraic stuff, where it's a very good survey by Fleming et al., which I think still is a good read. One thing that could be fun today, if you're up for it, is also as we're going over. So I'm going to present. I mean, I spent this now together with Kilian. We selected topics for 27 lectures, selected our favorites, and now I'm going to summarize. And it would be interesting to hear your favorites. I mean, also what things that we're missing, things that we could have covered, maybe think that we shouldn't have covered. So as we go over this and recap like what actually happened since we started in October, any kind of feedback, and yeah, it would have been nice to hear about this, or you're not mentioning this open problem. There might be some pretty embarrassing omissions here. Let's try to get them on the recording at least. So that this is intended to be kind of a bit of a forward-looking lecture. Where do we go from here? What good problems are there to work on? So we started with the resolution, which is, I think it's fair to say, I mean, it's a very well-studied proof system, but there's still lots of nice questions about it. We did some of the classics. We studied pigeonhole principle formulas, Satin formulas, encoding the graph handshake lemma, random KCNF formulas, field coloring formulas, proved classic hardness results. But we also did some more recent results. We talked about some trade-offs between different complexity measures, particularly we did not only talk about proof size or length for resolution, they're the same, but also about measures like width and different space measures. We talked about one of my favorite problems, which is proving resolution n to the k lower bound for a clique. This is still open. We went over the proof in some detail for regular resolution. And one other, of course, arguably one of the maybe most exciting results in proof complexity in the last decade or so is non-automatability. And we covered in some detail that resolution is not non-automatable, meaning you cannot search efficiently for resolution proofs. This is as hard as solving NP. And we saw that we had a wealth of proof complexity techniques, like proof techniques. And this is worth noting. We used the prosecutor-defendant game, which debate whether it's a technique, it's just a reformulation of resolution. But it's the case that Pavel Pudlak is doing in his proofs games paper is that why this is helpful for us is that somehow the human brain is geared towards playing games. So it's hard to think about how to syntactically come up with the resolution proof, but designing a prosecutor strategy is somehow psychologically easy. So it's really convenient to have this prosecutor-defendant game. We talked about random restrictions, about size with lower bounds, that it's sufficient to prove strong enough with lower bounds to get size lower bounds. Another classic result was this monotone feasible interpolation, that if the formula has the right structure, then we can extract a monotone circuit from a refutation of the formula. And then if we have a monotone circuit lower bound, then we get a proof complexity lower bound, which has been a very influential technique. And in the very last lecture, when we talked about non-automatability, we also talked about decision tree reductions. And I wanted to highlight that because one slightly interesting feature of proof complexity compared to many other areas of computation complexity theory is that there are reductions all over the place. I mean, that's how we build computational complexity theory, except proof complexity. There hasn't been that many reductions, but you can do decision tree reductions for resolution. We'll talk about, we didn't talk so much about it, but it also the analog for polynomial calculus, which we will get to, are low degree reductions. And it's sometimes really helpful to be able to do these reductions between different properties, different formats. And I think this is something that we probably haven't done enough, that it's worth looking into more. Something that we absolutely didn't talk about that would be great to talk about are pseudo-random generators. So these are, I'll mention later that we don't really have good candidates for hard formulas. I think, except random KCNFs, there's always a candidate, but it's kind of an unstructured and not so nice candidate for hardness. Pseudo-random generators are cleaner. So basically, you encode that you take some nice pseudo-random generator that stretches n bits to n plus 1 bits. And then you write down the claim that some particular length n plus 1 bit string is in the range of the pseudo-random generator. And now you know that for at least half of the possible ways of fixing this bit, this has to be a false claim. And if you could argue that if the pseudo-random generator is safe, then hopefully at least for proof systems such as polynomial calculus or resolution or cutting planes, this should be hard. So there has been some interesting results for resolution and some results also for polynomial calculus, but there it's already getting hard. So this is like an exciting topic that maybe we should have covered, but we didn't. One thing that we just to like for full consumer information, the proof complexity community has been obsessed a lot about looking at different types of resolution, not only tree-like resolution and regular resolution and general resolution, but all kinds of different shades in between and comparing their expressive power. There's a huge literature on this, which we just basically skip. One other thing that would have been nice to cover, which is far from non-obvious, and it was an open problem for quite a while, is if I now take a conflict-driven closed running solver, and we went over roughly how those work in the first lecture, can they search efficiently for resolution proofs? This is not obvious because CDCL solvers only find proofs with a very, very particular structure, but it was shown finally in 2 papers by Atserias, Fichte, and Thurley, and by Pippa, Trisov, and Norwich, that in fact, with at most a polynomial blowout, conflict-driven closed learning viewed as a proof system that faithfully models what CDCL algorithms do can actually simulate resolution. Now, we know that this has to be a CDCL viewed as a proof system result. If we could make this algorithmic, then we would break non-automatability. So there's some kind of non-determinism involved. In particular, the crucial piece of non-determinism that you need for this result is whenever you're making your branching decisions, when you're making variable assignments, you need to have full flexibility. We saw that width is perhaps somewhat surprisingly a really powerful tool for understanding resolution. If the width is asymptotically larger than or significantly larger than the square root of the number of variables, like number of variables times log number of variables, then you get super polynomial length lower bounds. What is more surprising is that also if we're focusing on KCNF formulas for simplicity, then actually width lower bounds immediately yield closed space lower bounds, and even the width squared is a lower bound on total space, where you count the total number of literals. The width has great explanatory power. We saw these results, but we also see that width can be almost optimally separated from closed space. So there are formulas that have constant width refutations, but require closed space asymptotically n over log n, which is linear closed space is worst case. And these were pairing formulas that we also encountered later during the course on many occasions. So the resolution space has been fairly well studied. There are some still fairly basic problems that we don't know the answer to. So we know that up to n over log n's closed space, it doesn't say anything about proof length, doesn't say anything about proof width. We don't have any example of formulas. The formulas that actually have linear closed space lower bounds, those are the exponentially hard formulas. And you could ask whether this is a coincidence or whether the fact that closed space and size is completely unrelated if it goes all the way up to linear. Like, are there formulas that are optimally hard for closed space that are still easy for length? Now we know that these can't be pebbling formulas, because if pebbling formulas are refutable in linear length, and then we know that the space is at most n over log n, so they would have to be something slightly different. Another curious question at the other extreme is, okay, suppose I tell you that a formula can be refuted in constant total space, so counting number of literals, spaces. Then, just by simple counting argument, that very proof has at most polynomial length. Why? Well, because we just look at the possible number of distinct configurations, and there's no need to repeat the configuration, and then this number is polynomial dominant. This counting argument does not work if I just tell you that it's constant closed space. So if I tell you that I have this formula, I have a proof in constant closed space, then we know that, oh, but if it's constant closed space and if it's KCNF formula, then it also has a proof in constant width, so it has a proof in polynomial length. But is it conceivable that the proof in constant closed space would have to be much longer than this, maybe even super polynomially large? This we don't know. And one other, we talked about some trade-off results. We talked about trade-offs between width and space. We talked about trade-offs about length and space. I don't think we talked about we didn't have time to talk about trade-offs between length and width, but it's also known that we know from Mendelssohn and Ridderson that if there's a short refutation, then there's a refutation in small width, but it's known by results from Papen and others that this can incur an exponent. When you minimize the width of the refutation, this can incur an exponential blow up in proof length. We know this is inherent. There are formulas for which this has to happen. We talked about supercritical trade-offs between length and space, formulas where they had short refutations, they had very, very space-efficient refutations in polylogarithmic clause space. But the short refutations had the property that they had superlinear, like large superlinear space. And if even bringing the space, even shaving, like say factor 2 or something off the clause space, so still super linear clause space, turn the proof length, the refutation length up to super polynomial. And the parameters of this result were very weak, so it would be nice to get stronger parameters. One thing that we didn't talk about is you also know that if I tell you that I have a proof in a resolution refutation with W, then for a formula over n variables, then the refutation length is at most n to the W. And we saw that this is tight. This proof in size n to the W, what's the space complexity of this? So suppose I insist on a proof in width W, can you tell me anything about the space complexity? In particular, could there be a supercritical trade-off there? So that if you want width W, then in fact your space will have to be n to the W. This, by Rasborov's hardness condensation technique, we know such a result, but only for formulas that are exponentially large, or formulas that grow larger than the n to the W. So it would be nice to have formulas of some constant polynomial size n to the big O of 1, and see, can you actually get a supercritical trade-off between width and clause space for such formulas? This is so. We don't fully understand the resolution complexity of so-called weak pigeonhole principal formulas, where the number of pigeons are significantly larger, like n squared, when the number of whole is n's. There have been some papers by Rasborov and also some papers by us that investigate this, even in the setting for graph pigeonhole principal formulas, and there are some results, but the results are not tight. One reason to care about these results are that the techniques are so nice or so intriguing. When you're looking at pigeonhole principal formulas with more than n squared pigeons, that's where the width lower bounds break down. The width lower bound still holds, but it doesn't tell you anything because the number of variables is too large. So Rasborov developed another technique that's called pseudo-width, that I would have loved to talk about. It would be great to talk about some other time, but we didn't have time to cover it. Clique lower bounds, as I already mentioned, even worst case clique lower bounds, that might be easier, even that would be interesting. And this is part of a broader program that I think Paul Beam and others were pursuing, like in the early years after the millennium. You can ask for, you can look at your, like your favorite NP complete problems, and you can ask, can we understand the proof complexity landscape for this? Like, how hard are these clique, coloring, or dominating set, and other Hamiltonian circuit, other nice problems for resolution? And you can say, well, we know that they're all NP complete. Yes, but these NP completeness reductions are too hard for resolution. So the fact that, for instance, that coloring is hard for resolution doesn't tell us anything about clique. So therefore, it's a meaningful question to ask, like whether you could build an NP completeness theory for resolution, for Kelvin planes, or for polynomial calculus, ideally with average case lower bounds. You have to be a bit careful though, because you can do it in the right, you can do it by cheating. Sometimes if you make your encodings evil enough or just naive enough, then you get lower bounds for the wrong reasons. For instance, for a Hamiltonian circuit, if you're not careful, then you can have an encoding where you somehow write down which vertex you're visiting at which time, and now you just say that I visit all vertices in half the time, and then you will basically map 2n pigeons to n holes. And since you're only using even time steps, then you remove all the Hamiltonicity constraints. Mm-hmm. And you still get a resolution lower bound, because resolution thinks that it's hard to prove that 2n pigeons don't happen to n holes. So then you should like that encode. So then we have a lower bound for Hamiltonicity, except that that's kind of the wrong lower bound. It's really just a Pigeonhole principle lower bound. So we should study a stronger encoding. And in fact, when people solve Hamiltonian circuit in constraint programming, for instance, then they do use stronger encodings where you have sort of you encode two things. You encode at which time step are you where, and then you also have like consistency constraints that says, well, if you're at two different time steps, if you're at some time step at some place, then the time step after you have to be at the neighbor. And then I think if you have these kind of encodings, then it's proving lower bound suddenly becomes a pretty hard problem. And one final problem that is pretty nice that actually it's Susanna Derizende has mentioned on several occasions. We do know that we have non-automatability results, which tells you how hard it is to search for reasonably short solutions. But now you can say, you can ask for even more. You can say, well, I want to find actually not just the reasonably short solution. I want to find the shortest proof. And how hard is that? I think that's a very nice question. And that is basically what we talked about regarding resolution and what we could have talked about but didn't talk about. So even though resolution is, I mean, there's still interesting questions, interesting problems remaining, I think, for resolution. Then we talked about algebraic proof systems. We didn't talk so much about Nullstellensatz because we're more interested in polynomial calculus. But for Nullstellensatz, also for polynomial calculus, traditionally people have cared most about the degree measure. The way to prove degree lower bounds for Nullstellensatz, the classic way, is to exhibit designs. And we did this in one of the last lectures, just made sure that we saw a design. So basically, this is something that maps all axioms to zero, all multiples of axioms to zero, but maps 1 to 1 and is linear. And that works for polynomials up to a degree d. And then you can prove, some of us prove that this is an if and only if a degree d lower bound only holds if you have such a design for polynomials up to degree d. We saw size degree trade-offs for Nullstellensatz, but they only worked if I didn't have dual variables. So no separate algebraic variables for x bar and y bar, so on. That's a little bit annoying. I think it would be nice to prove size degree trade-offs for Nullstellensatz with dual variables, but I think the results that we presented in class, they clearly cannot hold. And also without dual variables, the trade-offs we had were not super amazing, which turns out to be related to that we don't. So it turned out that Nullstellensatz size degree trade-offs for Pepping formulas was exactly the same as time space trade-offs for reversible Peppings, and we don't have so good reversible Pepping lower bounds. One final thing that we're going to talk about later is all of this relies heavily on the fact that we're insisting on representing polynomials as linear combinations of monomials. And you can ask, what if I have a better representation in mind? And we'll talk about it towards the end of today's lecture. The answer is that then you get to the ideal proof system, which is ridiculously strong. Because then somehow, then I don't know how you're representing your polynomials. And in order to know that you don't have a totally amazing representation, then it stands to reason that then I probably have a pretty good grasp of arithmetic circuit complexity. So it's important to be aware of that when we're talking about Nullstellensatz and also when we talk about polynomial calculus, we're really heavily relying on the fact that we're representing the polynomials as linear combinations of monomials. And this is just unavoidable because otherwise proving lower bounds is really, really hard. From an algorithmic point of view, this is not too much of a restriction in the sense that most tools will use this representation or will have to transition through this representation. So we didn't talk so much about Nullstellensatz. We talked more about polynomial calculus, which model Gröbner basis computations, which are heavily used in computational algebra. We saw that, or maybe we just claimed proof by intimidation, that polynomial calculus is exponentially stronger than resolution. To be a little bit careful, this assumes that we have formal separate variables for negated literals. Otherwise, it's known not to be true. So we do understand that for these algebraic proof systems, whether you throw in dual variables or not, most of the time, like, it doesn't matter for the lower bounds we prove, but we know that for Nullstellensatz and for polynomial calculus, adding dual variables actually increases the proof power in terms of proof size exponentially. For polynomial calculus, just as for Nullstellensatz, people have cared mostly about degree. How do we prove degree lower bounds? We prove them by pseudo-reductions, which are these operators that you somehow pretend that you're reducing modulo a polynomial ideal, and then Hilbert's Nordström says that your formula is satisfiable if and only if one, the multiplicative identity of the field, does not lie in your ideal. So somehow what pseudo-reductions do is that they piece together lots of different polynomial ideals that look locally consistent. One doesn't lie in any of the ideals. And as long as you can piece this together in a locally consistent way in low degree, then that's your degree lower bound. And then you get exactly the same results as for resolution for degree lower bounds that are larger than the square of the number of variables, assuming that the input is constant degree, then you get super polynomial size lower bounds. But as we saw, I mean, for resolution, we had this long list of tools that we can use. And for polynomial calculus, we don't have so much. In particular, we don't really have good tools that don't go via degree. So this is a weakness. We saw that some formulas that are hard for resolution are easy for polynomial calculus. If you're over GF2, then this is clear for Zeting formulas. The onto functional pigeonhole principle with n+1 pigeons and n holes is easy over any field, basically just because you count the number of holes and the number of pigeons, modulo the field characteristic, and you get different numbers, and polynomial calculus sees this. But other formulas are hard. If you want your Zeting lower bounds, then you write some kind of formula that counts mod P, where P is not your field characteristic. And then we saw that we got lower bounds for all fields for all other versions of the pigeonhole principle than the onto functional pigeonhole principle. Also for graph versions, if you restrict where the pigeons can fly. We saw lower bounds for random KCNF formulas, and also for coloring formulas, where the first lower bounds, which we did not see, was actually via low degree reduction. So once you know that the functional pigeonhole principle is hard over graphs, then you can sort of embed for a K, you can embed a K, if you have a pigeonhole principle over a K left regular expander graph, then you can embed this into a K coloring instance. But then what we saw was the more recent result that in fact we have average K lower bounds. Interestingly, these two results are somewhat incomparable. I mean, neither can prove the other. I tried to pitch also some algebraic, some algorithmic questions, where I just noted that when you actually use the Gröbner basis algorithm, you have to specify, you have to order your monomial somehow. And in proof complexity, this is not so explicit, and usually in the papers it looks like you're just ordering with respect to degree. In general, there are different orders. You can order lexicographically or degree lex or reverse degree lex and lots of other formulas. And this guides you, and then when you're adding up polynomials and canceling monomials, you're only allowed to do it with respect to this order. And I think one natural and nice question might be, could you compare in this way then polynomial calculus for different orders and see if you can separate them? This would be somewhat similar to the lower bounds we have for different subsystems of resolution. We know that that polynomial calculus with dual variables is exponentially more powerful. Unfortunately, Buchberger's algorithm for computing Gröbner bases does not work with dual variables. I think this is a very nice question, whether it would be somehow possible to take a Gröbner basis algorithm but make it aware of dual variables in some way, and see if this actually leads to exponential speedups. There are papers that actually show that when you do this, even in a somewhat hacky way, then you can really get performance improvements. And another favorite question, since I'm coming from the SAT side, is for the way, I mean, the reason that SAT solvers map to resolution is they don't think about resolution at all. They just assign variables and propagate, and then they hit the conflict, and then they do some kind of simple resolution derivations. Could you imagine such an algorithm, but that works on top of polynomial calculus instead of resolution? We do have this for cutting plates. We do have this for resolution. It's a little bit harder to see how to do it. Or if, I mean, there are ideas, but they're hard to get to. We did not talk about pseudo-random generators, where I think for polynomial calculus, that's right where it gets really, really hard. And there are some really, really good problems for pseudo-random generators in polynomial calculus. When we did our lower bounds, we actually only looked at techniques that works independently of which field we're in. So for instance, our techniques just said, oh, sating looks easy, which was just playing it safe, because we know that, well, in any other field than fields are characteristic too, sating is in fact hard, but we were not able to prove this. So we did not look at such techniques, which if you really want to claim that you know polynomial calculus, then arguably you should know this also. So for the way you prove lower bounds with sating, for instance, if you're in a field of characteristic that is not 2, then you do a shift of bases. So you map true to -1 and plus to 1. This is just an affine transformation, so it doesn't change the degree. But now the funny thing is that in this new basis, parity constraints are binomials. It's a monomial equal to plus -1. So monomial -1 or +1 equals 0. Just a binomial constraint. And then you can show that when you're working with binomials without loss of generality, your whole polynomial calculus derivation is only going to derive binomials. Because if it derives something else, then you'll simplify and just keep binomials around. And that makes it easier to analyze the structure, and then you can prove a very strong degree lower bound in this so-called Fourier basis, when true is -1 and false is 1. And then you use that, well, we only did an affine shift, so degree didn't change. So now we go back to 0, 1, where the same degree lower bound must hold. And now you use in Pagliazzo-Bullak-Skal that says that, well, your degree lower bound is so strong now, you have a linear degree lower bound. So clearly you have an exponential size lower bound. This we didn't cover. We also didn't cover, there's a version of this. We talked about constraint variable incidence graphs and how to analyze them. There is a field-dependent version of this which looks at what your constraints look like. And in particular, if the constraints have high immunity, and a constraint has high immunity if it has no low-degree implications. And the reason that we didn't have to care about this so much is that clauses are very immune. If you think of a clause with D, doesn't imply any polynomial of degree smaller than D. And this is sort of somehow under the hood was useful for us. But now you can generalize this and say, okay, what if I don't have D, but I have some kind of strong immunity lower bound? With respect to the field I'm in, maybe I'm not immune over every field, but the field we're interested in, can I use this to prove a lower bound? The answer is yes, and this is something that Alekhnovich and Nordström, which would be nice to talk about. We didn't talk about it. And one technical challenge is that suppose you would want to combine what we did, where we grouped some of the constraints together, and then we somehow said that we put some constraints on the side and say they just filter what truth value assignments we're interested in. This does not play well with the Alekhnovich-Kasparov immunity. This is a technical challenge. It would be nice to combine the two and see if they could somehow be made into the same technique. There are degree lower bounds that we don't know how to prove, but we have resolution with lower bounds, but we don't have corresponding polynomial calculus lower bounds. The dense linear ordering formula, I think I mentioned, and there are some homomorphism problems. So coloring can be viewed as a homomorphism mapping, and saying that the graph is not colored means that it cannot map. A graph is not k-colorable basically if it doesn't map homomorphically to the complete graph over k vertices. Now you can generalize this and ask for lower bounds. And again, we know and understand this much, much better for resolution than for polynomial calculus. Pseudo-random generators I already mentioned. Size lower bounds without using degree. So for resolution, we still have exponential lower bounds for the weak pigeon principle. Maybe I didn't say this clearly enough. So interestingly, all the way up to an exponential number of pigeons and just n holes, we have exponential lower bounds for resolution. So like all the basic, yeah. So even if you make the claim in resolution that an exponential number of pigeons fits into a linear number of holes, resolution still struggles with this. For polynomial calculus, we have no lower bounds above n squared pigeons. And of course, we have no lower bounds for clique formulas. And they are sort of, they're similar in the sense that for both of these formulas, it's clear that degree lower bounds will not have this. So my take on this, I like polynomial calculus is one of my favorite proof systems. I think there are so many good problems for polynomial calculus. Even if you just care about, the classic proof complexity measure of size, which you can attack via degree, there are like tons of really good problems. The interesting thing, and if you're a bit more broad-minded and you're also willing to consider space complexity, then there are tons of open problems. We talked about closed space for resolution. This naturally, sort of the natural analog is monomial space, the number of monomials. We don't even know whether monomial space for polynomial calculus, whether polynomial calculus is stronger measured in terms of monomial space than resolution is measured in terms of closed space. We have no idea. We strongly suspect that for taking formulas over expanders and for, say, functional pigeonhole principal formulas, we should have optimal linear monomial space lower bounds. This is open. All we have is this Galici-Kolodjezhik-Tappen paper that says that monomial space is at least square root of resolution width, and therefore you get square root and lower bounds. Now, in special cases, we have better bounds. For taking formulas, for instance, I can take any expander graph, and then I can turn it into a multigraph by adding 2 copies of every edge. And now I get an optimal linear monomial space lower bounds. So this means that this has this slightly bizarre consequence that if I take a 3 regular expander graph and make it into a 6 regular graph, pretty crappy expander by just adding double copies of every edge, then we can prove a optimal linear width lower bound. But if I take just a 6 regular expander, then we can only prove square root and lower bound. And this is a little bit bizarre. It would be, and as you mentioned in class when we had this lecture, of course, the easiest way of fixing this would be to simply say, well, why don't we prove that monomial space is greater or equal resolution width period? And yes, that would be great. Another favorite problem that would not follow from this is monomial space lower bounds for pebbling formulas would be really nice. There's really no reason, I think, to believe other than that the black-white pebbling price of a graph should be a lower bound for monomial space also. But I have no idea how to prove this, or at least I tried and failed. We also remember for resolution, we knew that width and closed space are completely uncorrelated. In the sense that width can be constant and closed space essentially maximal, n over log n. We do have an even stronger separation for polynomial calculus. Degree can be constant and monomial space can be linear. but this separation depends on the characteristic. We don't have any characteristic independent such strong separation. Supercritical size space trade-offs, you can get similar results to those we have for resolution, but they using Zekin formulas, so they won't hold in characteristic. For resolution, we saw that we had optimal total space lower bounds and square total space lower bounds. I don't think we have any total space lower bounds for polynomial calculus, except for exponentially large formulas. In the very first paper, like if you allow yourself to make your formulas exponentially large, then you can prove n squared total space lower bounds where n is the number of variables, but only for exponentially large formulas, which is kind of cheating. And what is interesting is that for some of these problems, all I'm saying now holds for polynomial calculus with dual variables. Some of these problems are easier and have been solved if you don't have dual variables, which is also a little bit weird because usually dual variables or not doesn't matter. Here is an example where somehow space lower bounds are sometimes much easier if you don't have dual. I think the last thing we did for polynomial calculus was to say, well, what if you are not over 0, 1? What if you're encoding things in some other way? For instance, maybe -1 is true and +1 is false, or maybe you're doing coloring and then k coloring, and then it's natural to be over a field where you have a primitive kth root of unity, and then the power of the root of unity could be like the color of your vertex. So we looked at some degree, so there now we know that degree lower bounds will obviously not give you size lower bounds, because over the ±1 basis we have the same degree lower bound for Zekin, but obviously not a size lower bound over ±1. For some formulas like pigeonhole principle, we do have lower bounds. We also have lower bounds for formulas where you lift with the right type of gadgets, but they are, as you saw, they're kind of technically a bit confusing and intriguing and weird in different ways. In particular, one thing is that you, in order for these proofs to work for pigeonhole principle, for instance, you need to consider the whole family. Like when we do resolution and standard polynomial calculus, we know that if I have a width or degree lower bound for a formula, then I get a size lower bound for that particular formula. And now I'm good to go. We were not able to get that for polynomial calculus over roots of unity. There you have to say somehow, I'm thinking about this whole family. And then we used standard polynomial calculus tools to say we have strong degree lower bounds for this whole family. And then we said, suppose that we have small proofs, small refutations for some formula, and we massaged it heavily and changed it. And then finally, we got a low degree refutation for a much, much, much smaller copy of the formula, but from the same family. And then we use that degree lower bound. And that is somehow different, that we have to go via this whole family. It's not clear to me whether that should be necessary. So in particular, it would be, I mean, somehow for both resolution and for polynomial calculus, we have statements that say something like the following. Suppose I have an input. It has typically constant degree. You look at the constraint variable incidence graph, and you see that it's an expander. And then the constraints have to be somewhat nice. For instance, they're clauses, or they have to be immune, or otherwise we have these respectful edges for polynomial calculus. So some property P. So basically we said that look at the closed variable incidence graph. If it is an expander and if the constraint have property P, then we're good to go. Okay. It would be nice, I think, to have that type of result for polynomial calculus over roots of unity. One thing that one can also note is that actually one way of viewing the transition from 0, 1 to roots of unity is you can do this by introducing extension variables. So you can actually let polynomial calculus work in both bases at the same time. So this is a way of equipping polynomial calculus with a limited power to introduce extension variables. And we know in general, and we'll remind ourselves after the break probably, that extension variables in general are extremely powerful, but here we're just getting like a limited amount of extensions, and can still prove lower bounds. So there are lower bounds where you have polynomial calculus and it can flip as it wishes between 0, 1 and roots of unity, and still we have exponential lower bounds. It would be very interesting to see if one could extend this to even stronger settings. And there are some results along these lines, and unfortunately in some of the latest papers there are some claims that seem to be a little bit problematic. So doing this in general still appears to be open. And then one other thing that I just don't know is whether it makes sense to think about monomial space lower bounds for polynomial calculus over roots of unity. I haven't thought about that at all. Maybe someone should think about that. I don't know. So yeah, so we in this course we focused on resolution. Then we talked about algebraic proof systems, a little bit about Nordström, but mostly about polynomial calculus. And the third main theme was cutting planes, which models 0-1 integer linear programming. We know that it's exponentially stronger than resolution. We didn't show this, but it's incomparable to polynomial calculus. I think the way you show this is, well, cutting planes is stronger than polynomial calculus because it can count. So the pigeonhole principles are hard for polynomial calculus, they're easy for cutting planes. In the other direction, I think you need to use the lifting machinery that Kilian showed, where polynomial calculus will be able to deal with some formulas, but where if you have large resolution with Garg, Kamat, and Sokolov showed that the cutting plane's size is exponential. I think so cutting planes and polynomial calculus are incomparable, and I think what we managed to impress on you is that somehow it was much more challenging to prove cutting planes lower bounds. When we got to polynomial calculus, there was cutting planes, there was a lot of pain involved, and we I think like for polynomial calculus and resolution, most of the proofs we did like everything honestly, and you saw everything. For cutting planes, I think it's sweeping more and more under the rug. The proof techniques that we saw was monotone feasible interpolation. For a very long time, that was pretty much the only game in town. So recently, there have been, I mean, you can get some results. In particular, you can get tree-like lower bounds. And as we saw, you can also get trade-offs from lifting theorems in standard, in classic communication complexity. Some of the most exciting, very recent results are studying DAG-like communication complexity, where for cutting planes, your DAG-like real communication is essentially the same thing as real circuits, but you view them with like communication complexity classes. And some of those, like most advanced lifting theorems that are on the market today can then be used to prove cutting planes lower bounds. And we also saw, I think, a very interesting paper by Sokolov, which recovers the lower bound for random log and CNF formulas via some kind of bottleneck counting argument. And I think it's a good question to like, could we really understand what this proof is doing? Can it do anything more interesting? Yeah, I think for cutting planes for a long time, we have had a lack of tools. Now there are new tools appearing. Can we understand them? Can we refine them further? This is very interesting also. So cutting planes is tightly related to communication complexity and lifting. So one way of improving many of the results would be to simply have stronger lifting results. For instance, when you're lifting with the indexing gadget, if you remember, like Alice had an index and every bit of the original formula was expanded into m bits for Bob, and Alex had an index saying which bit we're using. M was typically ridiculously large. Like some, in the first papers, it was like m to the, I don't know, even a 3-digit number maybe. Then I think you can bring it down to, where now you can almost bring it down to linear, but it's like sublinear or even constant would be fantastic. Yeah, but this is a big open problem even in communication. You could say it would be nice to deal with non-lifted formulas. For instance, can I just, with my bare hand, prove coloring or click lower bounds? Then maybe it's not so clear whether you can use lifting, at least not probably in the average case. So who knows? One other annoying fact or challenging fact for cutting planes is that most lower bounds technique, they just operate with, I have two constraints and I know that you combine them somehow. They imply this third constraint. So the lower bounds we get hold in a very strong semantic setting. In a semantic setting where, for instance, you can solve subset sum in a single step, because if you have an infeasible subset sum instance, then you have the less equal and greater equal constraints, they're infeasible, and then you get contradiction in one step. And the lower bound techniques that we have work even in that setting, which kind of tells us also then maybe why we're struggling so much to prove lower bounds. So one thing that would maybe be helpful is if we could develop techniques that would look at actually syntactically what is cutting planes actually able to derive. Not this worst case, well, it is implied, but more like, yeah, I mean, because we believe subset sum is probably hard, for instance. So our current lower bound techniques are somehow inherently not able to prove this. And another thing that we can't do that is interesting from an algorithmic point of view, I think we can do it to a limited extent, like with ad hoc methods. But for instance, compare different types of cuts. There are division cuts, the Quattal-Gomori standard cuts. There are also so-called mixed integer rounding cuts or coefficient tightening. There are zero half cuts. The operations research literature has a lot of different cuts that you can use to define different types of cutting planes proof system. It's an interesting proof complexity theoretic question, how the strength of these different subsystems would compare. In order to answer this question, we would need a more refined understanding of cutting planes than just saying, I got this linear inequality because it was implied. Then you can never see, like, syntactically how it was derived. Lower bound for random KCNF formulas where k is smaller than log n is a big open problem, but I think it's believed to be very hard. One of the last lectures we had, we discussed what happens if I take cutting planes, but I insist that all my coefficients should only have a logarithmic number of bits. So all my coefficients have at most polynomial magnitude. This proof system is often referred to as CP star. It has been open for more than 30 years now, whether cutting planes with polynomially bounded coefficients is as strong as general cutting planes up to polynomial factors, or whether there in fact is a separation. What we saw, we saw ingredients in a proof showing that we still don't know this, but at least now we know, which we didn't know before, that there are size space trade-offs that apply to CP star that don't apply to general cutting plane. So there are, we can prove there are some non-trivial things that that cutting planes with polynomially bounded coefficients cannot do efficiently that general cutting planes can do efficiently. Again, for space, I spent too many of the early years of my career trying to prove line space lower bounds, where we measure, again, the natural analog to clause space is in polynomial calculus, it is to count the number of monomials, because that's what the size measure counts. In cutting planes, the natural measure is like the number of inequalities. So you can try to prove inequality space lower bounds or line space lower bounds. I failed miserably at doing this. And Galicia, Kudlak, and Tapan explained why when they showed that, in fact, line space 5 is sufficient to refute anything. But such proofs require, or the proofs that they show, they will have exponentially large coefficients. Which raises the question of, well, suppose I insist on polynomially bounded coefficients. Can we then actually prove non-trivial line space lower bounds? The trade-offs that we had for CP star that didn't apply to general cutting planes were not true trade-offs. They are probably maybe conditional space lower bounds, for all I know. It would be interesting to see if we could actually prove true trade-offs, if we could exhibit formulas where we show that they have small proofs in CP star, they have space-efficient proofs in CP star, but there's a trade-off between the two. This we still don't know. So this is open. Related to this would be proving such a result, at least for pebbling formulas, would also probably imply some kind of algorithmic version of a parity decision tree lower bound. So this is a very nice, very concrete problem. We know that if you look at the falsified clause search program for a pebbling formula, and look at a standard decision tree that just can query variables until it has a violated clause, we know that the query complexity for standard decision trees is exactly the same. There's no slap as for the much more general computational model where we have parity decision trees. We don't have a good proof of this in the sense that for standard decision trees, if you start asking me queries, then I can respond to them in an online fashion. Without knowing where you're going, I can sort of compute the correct answers that will keep you going for the right number of steps. For parity decision trees, I have no idea how to answer. I just know that there must be some way of doing it because we have a proof that the parity decision tree complexity is exactly the same as the decision tree complexity. This we know, but we have no idea why. Like I cannot algorithmically answer parity queries. And if we want to prove stronger trade-offs, then in particular that would imply communication complexity lower bounds. And if we have communication complexity lower bounds, those lower bounds would in particular apply against when Alice and Bob use a parity decision tree to build a protocol, which they can efficiently. So if we would prove like better communication complexity lower bounds or better CP star trade-offs, then sort of a necessary condition for doing this is in particular such a result would prove that in some algorithmically concrete way, hopefully, that parity decision trees, like why parity decision trees don't solve this efficiently. So we don't have like a round efficient version of this. And also one thing that is related to the cutting plane size space trade-off result that we saw where we did the Gös-Pitassi-Watson celebrated lifting paper, but we added round efficiency. I think it's an interesting question to ask for other types of lifting theorems. Where could you potentially get new applications if you made these simulation theorems round efficient? And we saw the size space trade-offs for general cutting planes, but the parameters were pretty crappy. Again, because of the parameters of the lifting, it would be nice to improve this. So finally, because this is close to my heart, I guess, as I said, so for cutting planes, we actually do have SAT-based techniques. So there are so-called pseudo-Boolean solvers that basically use SAT-inspired techniques, but in the cutting planes proof system to solve SAT problems, to even solve 0-1 ILPs. But it turns out that algorithmically this is much more complicated than conflict-driven close learning. For all kinds of reasons, when you have 0-1 linear inequalities, a big part of the algorithm will set variables to values and then propagate. This is much harder for 0-1 linear inequalities than closes. If you're not careful, your coefficient sizes will explode, and then integer arithmetic gets very expensive. Also, how do you, when you're choosing, should I derive this or should I derive that? For clauses, you could argue that somehow, this is not quite true, but you could compare two clauses and say, for instance, a smaller clause seems to be clearly better. But how do you compare, like for a general 0-1 integer linear inequality, there are sort of several dimensions in which you can compare. And just looking at these two constraints and say which one is better is already that a difficult question. How to do conflict analysis, like once you've assigned your variables and now you hit a violated constraint and you want to derive, you want to analyze the conflict, this is a very interesting question. What is a good way of employing cutting planes to derive new constraints, which is also related to the question of, well, if I don't know what a good constraint is, then how do I know if I derived a good constraint? And then one problem is that is very annoying, that also the state-of-the-art pseudo-Boolean solvers that we have today, if you want to kill them, you just give them CNF input, because then they generate to conflict-driven closed learning, but with very expensive data structure. So for instance, we know that cutting planes can refute the pigeonhole principle in CNF efficiently. Pseudo-Boolean solvers cannot. They will run an exponential time. So what would be, of course, you can fix this in the sense that you could have some kind of naive detection that, do I have a pigeonhole principle instance here? And then you could like rewrite it, right? And you can try to code this up, and yes, it works. But it would be very interesting to in a more general principled way, sort of, as you're running your solver, which has to run really, really fast, can you discover that I have a set of CNF formulas here that I think I could rewrite to this linear inequality, and it would be much nicer? This is a quite an interesting algorithmic challenge. There have been papers on this, but nothing has been good enough to actually use in practice. So I'm thinking that this is basically what you've learned. So I'd suggest maybe this is a good place to take a break. I think we're more than halfway through, but let's see. And then we'll talk a little bit about what we didn't learn, but what we maybe should learn next time a course like this is given. You should tell me that maybe we should have focused on these other things instead, or had a slightly different balance, or what do I know. But after the break, I want to talk about stabbing planes, semi-algebraic proof systems such as Real-Adams and sums of squares, resolution over parities. All of these are like things that we could have done instead. It was really a choice of our priorities. Did we get them right? I'm not sure. And then I want to talk a little bit also about things like Frege, extended Frege, the ideal proof system, which we never intended to cover, also because then we get to so strong proof systems that we just don't have unconditional orders. But that will do after the break. Okay, now let's talk about things that we did not talk about but could have talked about. Stabbing planes is, I already said that cutting planes is meant to model 0-1 integer linear programming solving, except that stabbing planes is arguably a slightly better model. I'm very consciously skipping the most definitions today because I think you've seen them before, but now we're getting to proof systems that we didn't see so much. So let's just make a quick recap. Basically, a stabbing planes proof is a decision tree, but you're branching over linear inequalities. And the whole point is that on one branch, so you're branching over a linear form, but you can branch over, is this greater equal A, or otherwise it's less equal A minus 1. And this is why it's stabbing the plane. There will be some slab in the middle that this branching is ruling out, namely the integer slab between A and A minus 1. So you have your decision tree, and then in every node, linear programming is for free, which is true in the sense that that's exactly what, like in every branching node in a MIP solver, you would solve not just one linear program, you would solve tons of linear programs. Which means that all you need to do is you need to branch, and then as soon as your LP is infeasible, you're good. And this is not so hard to prove, that this simulates cutting planes efficiently, though not with respect to depth. It was originally believed to be much stronger than cutting planes, I think. You read the early papers and the way the discussions were going in the community. But then there were some somewhat surprising papers that showed that, in fact, if you have a stabbing planes proof, you have like stabbing planes star. Okay, so stabbing planes with polynomially bounded coefficients, then in particular, this can be somewhat efficiently simulated by cutting planes. What does somewhat efficiently mean? Somewhat efficiently means, firstly, I want arbitrarily, possibly exponentially large coefficients in cutting planes, and we won't quite do polynomial time, but at least quasi polynomial size, but quasi polynomial size. And that is already, I mean, quasi polynomial or polynomial. I mean, in proof complexity, quasi polynomial is closer to polynomial than to exponential, or maybe, you know, in any branch of proof complexity. So this is sort of saying that, okay, at least stabbing plane star is very close to cutting planes. And then even more recently, there have been lower bounds for stabbing planes via interpolation. So lifting some of the strong exponential lower bounds we had for cutting planes to stabbing planes. So I don't know if people are sure now what to believe about stabbing planes and cutting planes. This is a great question. Like, how are they actually related? And something we maybe should have talked about. Nullstellensatz, so here is the Nordström definition. So we're assuming Boolean variables. So x squared minus x for any variable should value to 0. You can multiply these Boolean axioms by polynomials. And then we have a bunch of input polynomials p, which you can also multiply by polynomials. You can do it, you should do it in such a way that syntactically you get 1. That's a Hilbert's Nullstellensatz says that this is possible if and only if there is no common root of these polynomials, because we're over 0, 1. And so Nullstellensatz certificate is such a certificate. And then instead of 1, I just changed it to -1 because it's nicer when I say in Shirley-Adams, you sort of have a Nullstellensatz certificate, except that you're also allowed to add any monomials, 1 minus xi times xj, or I guess they're called sometimes conical juntas or something, cones or something like this. So the point is that these guys will obviously be non-negative. So they can only bring you further, and the alphas are all positive. So you can only get further from -1 in this way. So every Nullstellensatz proof is a Shirley-Adams proof, but the opposite does not hold. And then sums of squares is even stronger. You're not just allowed to add positive linear combinations of monomials, but any sum of squares. So any Shirley-Adams proofs is a sum of square proofs, but not the other way around. And Shirley-Adams and sums of squares are then known as semi-algebraic proof systems. Yes.
So basically, you take Nullstellensatz and then you take a family of polynomials that you know will be positive, and you say, I'm allowed to add this to my proof.
You could, yeah, sure.
So can we look at other families of polynomials that are not conical juntas or sum of squares?
That's a great question.
You can do that? Because I think the theorem is a bit more finicky than this, but maybe not. Maybe you can do every positive.
We're talking about, so Stengel's, Stengel's positive Stellensatz.
Yes.
But does it have like quantitative? Because I guess we care about, I mean, Nullstellensatz doesn't need this thing, right? The only thing it can do, it can bring down the, what can we do now? We can bring down the degree substantially, and we can also bring down the size of the proof substantially. But Nullstellensatz is complete, right? So it's not like we're able to refute more things with sums of squares, but we can do it much more efficiently.
Yeah, okay. I'm sure there's some other family that would be better.
It's a good question. I don't know. I'm a little bit out of my, I haven't actively worked on this, which is one reason why it would be exciting to talk more about them than I would learn stuff. So where do they come from? Well, they model, if you start, Shirley-Adams is basically, if you start with an LP model of your problem, but it is a Boolean problem, then Shirley-Adams gives you a systematic way of strengthening your LP to cut away more and more fractional points. So it's known for Shirley-Adams is that Shirley-Adams in like degree n is solving a Boolean problem, but potentially at a price of an exponential blow-up. And sum of squares is kind of the same, but for so-called semi-definite programming, which I won't even go into. Except I should say for sum of squares that this is a very hot topic, for instance, if you're into approximation of NP-hard problems. Many of the best, because for many problems, you can phrase them as the problem of finding a low degree sum of squares certificate. which you can often do efficiently. We're getting we don't really have time to go into details here, but so basically you can search efficiently, except for finicky details that I'm really sweeping under the rug in the most shameless of ways. But often you can search efficiently for low degree sums of squares certificates, and that gives you very strong algorithms. And some of the best algorithms we have for NP complete problems can be obtained in this way, except a slightly weird thing that counting parities is like really, really hard for sum of squares. So many of the lower bounds we have are built on the workhorse that you some way or other you reduce it to Satan formulas, and then you know that Satan formulas are just impossible for sum of squares. This is not fully satisfying, but this is the way it is. It's known that, well, we already saw sort of syntactically that Nullstellensatz, Schreyer-Adams, and sum of squares form a hierarchy. This hierarchy is strict. More surprisingly, sum of squares is strictly stronger than polynomial calculus, which is so all of these, just to point out that these are so-called static proof systems. It just like talking about space wouldn't make sense here, right? Because if the proof is what it is, you write it down one shot. These are so-called static proof system, whereas polynomial calculus is a dynamic proof system that builds things up step by step. Nevertheless, sum of squares is strictly stronger than the polynomial calculus proof systems, assuming that you're in the same field, which means that sum of squares can only live in the field of reals because you want an ordered field. Obviously, if you're over GF2, then polynomial calculus over GF2 can be stronger than sum of squares over the reals, but because it's ATBCC. Schreyer-Adams and polynomial calculus are incomparable. So both of these results are by Berkowitz. I think it's fair to say that they made quite a splash at the time. We're not expecting. Very interestingly, so you can look at all of these. You can look at cutting planes, stabbing planes, Schreyer-Adams, Nullstellensatz over the reals, and you can ask, how much do I care about the size of the coefficients? And does that change the power of the proof system? And most of the time, we don't know. I mean, we talked about for cutting planes, we really don't know. The only thing we can get are some kind of trade-offs that hold in one setting but not the other. But a couple of years ago, in fact, for Schreyer-Adams, we do know a separation. So for Schreyer-Adams, you can define Schreyer-Adams star, which is Schreyer-Adams with polynomially bounded coefficients, except that it's typically called unary Schreyer-Adams. It's Schreyer-Adams where I force you to write down the coefficients in unary, and you should still have a polynomial size proof. That's kind of the same thing as saying, oh, your coefficients should have at most a logarithmic number of bits. So there is a separation between unary Schreyer-Adams and Schreyer-Adams. In fact, I think between unary Schreyer-Adams and resolution even. For sums of squares, I don't think we know this. There are clique lower bounds for unary Schreyer-Adams by Susanna de Resende and Kilian Risse together with Aaron Poteke. Aaron also has average case coloring lower bounds, but I think the parameters are nowhere as good as they are for polynomial calculus. So, I mean, clique lower bounds for Schreyer-Adams without the unary would be fantastic. Better coloring lower bounds for sum of squares would be fantastic. Just as for resolution and polynomial calculus, we know that strong enough degree lower bounds imply size lower bounds. That's by Atsiras and Hakoniemi. I don't think we know whether there are size degree trade-offs, which we do know for resolution and for polynomial calculus. For both polynomial calculus and resolution, we know that if there is a small proof, you can bring the degree / width down, but at the cost of exponentially blowing up the size. And we don't know that this has to be so for Schreyer-Adams or sum of squares. We also do not have non-automatability results for Schreyer-Adams and sum of squares. I mean, I think by now it's kind of clear that it would be very surprising if they were automatable, but it's excellent questions, excellent problems, but maybe hard. Something that many of you will be aware of as another area that has seen a lot of action is you take the resolution proof system, but instead of clauses, you now have disjunction over parity constraints. And why are people so interested in this? I don't know about you, but the first time I saw resolution over parities, I found it extremely artificial and I was very annoyed. It's sort of an acquired taste, or was at least for me. The reason why it's so interesting is, as we will see, or talk about more in a minute, it is the first obstacle on the way towards going beyond lower bounds for bounded depth frege. So it's really like right at where proof complexity is stuck, where we really can get no further. It's one of the extremely concrete barriers where like where we really have the research frontier. And that's why it's so interesting, and it's very exciting that things have been moving. There have been a lot of papers recently proving super polynomial size lower bounds, unfortunately only for resolution over parities refutations of bounded depth, where I think there seems to be a barrier somewhere around quadratic depth. And there's also a relation to lifting here in the sense that many of the tools and techniques sort of come from lifting, have a lifting-like flavor, and sort of a trivial observation is that, well, if you could, in these models, if you could get DAG-like lifting, then you would have like resolution over parities, lower bounds without any depth restrictions. But this is not known how to do. So those are all things that we could have done, but didn't. And where it would be interesting, and I don't know, maybe we'll have an evaluation later, like it would be generally interesting to hear your comments and your views, like did we get our priorities strict, or should we maybe have done more of this and less of resolution, or I don't know. Like we made the choices we made, mostly I, but Kilian was definitely partly guilty at least. We could have made different choices. It would be interesting to hear what you think about this. Something that we've never really seriously thought about covering, though, was Frege proof systems. What is a Frege proof system? Usually the first problem when you want to study a Frege proof system is you often like you don't even find the definition. And the reason for this is that a Frege system is anything you were taught in your first logic class. Like any system for natural deduction is Frege. Why don't I care? Well, because there's a very general theorem proving that any way of setting up your Frege proof system is polynomial equivalent. So there are lots of different ways of setting up Frege proof systems. They're all the same up to polynomial. Frege proof systems seem way too strong for what we can prove lower bounds for. And I think it's also fair to say that it's not even clear, I think, if we have good lower bound candidates. So random K-CNFs, yes, of course. Maybe pseudo-random generator formulas, but then you have the paradox somehow that the formulas that are hard enough to be hard are also very hard to understand well enough to prove lower bounds for. So I think it's believable that pseudo-random generator formulas should be hard for Frege, maybe. But we cannot even prove such lower bounds currently in the way we would like for polynomial calculus. So, Frege might be some way out. One thing that you can try to do, and I think a lot of people in proof complexity do, which we didn't think about covering at all because somehow we were raised in the KTH tradition up in Stockholm, both I and Susanna and Kilian, where you sort of prove unconditional lower bounds. That's what you do. But of course, a lot of computational complexity theory does if pigs can fly, then horses can whistle style type of theorems. And you can ask if you can do this also for stronger proof systems. Like basically, can you make some assumption that is interesting and then prove Frege lower bounds based on this assumption? Now, ideally, this should be an interesting assumption. It should not be the assumption NP distinct from co-NP in disguise. Something slightly more interesting. There have been, as we talked about when we talked about automatability, there are some lower bounds under cryptographic assumptions, which I guess technically speaking, don't imply NP distinct from co-NP, but they're certainly very strong in other ways. So, yeah, I don't know. It becomes a matter of taste, like what kind of assumptions would be happy with. In any case, I profess kind of ignorance in this area. I've never worked on these type of conditional results, but they are certainly interesting and valid, and you could make the argument that if you want to understand Frege, then maybe this is the way to go. If we want unconditional lower bounds, then we can look at bounded depth Frege, which is Frege proof systems, but now I limit the depth of my formulas. The most drastic restriction of my depth would be to say depth 1 or 0, depending on how you count. That's resolution. You can go one step up and look at DNF resolution, in particular KDNF resolution, which is basically resolution, but instead of disjunctions over literals, you have disjunction over conjunctions. So the lines in your proofs are DNF formulas. And then typically you limit K to be constant or logarithmic, and then you have KDNF resolution. We know that random KCNF formulas are hard for KDNF resolution. This is, yeah, where the Ks are different. The KDNF resolution K and the random KCNF formula K are different, or should be fixed maybe. This is already like a highly non-trivial result, which could be fun to go over. Weak pigeonhole principal formulas are not well understood at all. And there was quite intense study of this, I don't remember, 10, 15 years ago, maybe. I don't know if people just gave up. The most important tool is still random restrictions, except in resolution and in polynomial calculus, you can hope that your random restriction sets a variable correctly, and then the monomial or the clause just vanishes. It gets satisfied and it disappears. This will not happen in general for a DNF formula. What you can hope for is maybe a collapse, that a DNF sort of collapses to a CNF. But in general, you can't hope to just satisfy it. And this brings us to a notion of what is called switching lemmas, and this is a more general thing for bounded depth Frege, that the tool of choice to prove lower bounds is you basically do repeated random restrictions, and then you want to argue basically that every time you hit the formula with a random restriction, the depth of the formula collapses one level, kind of. I'm seriously lying here, but this is sort of how it goes. It gets technically very, very complicated. So for bounded depth Frege, which are formulas of not depth 2, not DNF formulas, but arbitrary depth, we know that the pigeonhole principle is hard for n plus 1 pigeons and n holes. But I think already for 2n pigeons, actually bounded depth Frege knows 2n is far away enough from n that bounded depth Frege says, no, these numbers look different. Like you can do approximate counting. And I think what is not understood is like how approximate counting can KDNF resolution do. With the caveat that I'm not super on top of the literature here, but I do think it's not well understood for KDNF resolution. Proving lower bounds for random KCNF formulas is a major open challenge. Random K-XOR formulas even more so, which is a little bit interesting, because if you take random K-XOR formulas and you throw in even more structure, you restrict them even more so that they have to be sating formulas, then we can actually prove lower bounds. So somehow the fact that your XOR constraints come with a graph attached, which actually makes it more constrained, also makes it easier to prove the lower bound. Bounded depth Frege, there has been some recent developments on bounded depth Frege in papers by Johan Hostad, also with Kilian Risse. So I think one thing that could be interesting to do is to study these papers and try to understand. There's like the problems that remain are probably difficult, but it's also the case that there have been powerful new tools developed quite recently. So there might be room for making progress. Another thing that is relevant to know for bounded depth Frege is that there's this sort of moral parallels with circuit complexity. there are, for some proof systems, you can sort of map them to circuit models in the sense that you could say that sort of Frege talks about general formulas in circuit complexity. Bounded depth circuits is kind of bounded depth Frege. Bounded depth circuits with mod gates is kind of Frege with modular connectives, or say parity connectives for concreteness. And there is a certain transfer of tools and techniques from the circuit side to the proof complexity side. Now, the interesting thing here is that proof complexity gets, there are also, like, you can define, I mean, also people study threshold circuits, and you can also sort of define threshold proof systems over on the proof complexity side, which would be maybe like high degree versions of cutting planes, if you will. Okay. The interesting thing is that proof complexity, circuit complexity, long ago proved bounded depth circuit lower bounds. And then Razborov-Smolensky extended these strong lower bounds also to ACC0 circuits, so bounded depth with mod gates. Proof complexity never managed to take the step from bounded depth to bounded depth with mod gates. And it's not clear why. So there's, I don't think we're able to articulate a clear reason why we're not able to follow circuit complexity. And that is the reason why, in particular, resolution with parities is such an interesting proof system. Because if we could prove lower bounds for bounded depth Frege with mod connectives, then in particular, clearly we could do resolution with parities. But we can. And the one technical challenge is, okay, so how do you prove the bounded depth circuit lower bounds? You use different type of switching lemmas, or for ACC0, you use the approximation method. We don't get the approximation method to work somehow over in proof complexity. And the switching lemmas, if you compare the switching lemmas for bounded depth circuits and the switching lemmas for bounded depth Frege, the bounded depth Frege switching lemmas are just way more complicated. And I think if you talk to people who are working on this, the feeling is that we need something other than switching lemmas. Because the switching lemmas, one problem is also that you need to, the restrictions have to be really, really aggressive. You're setting most of your variables, and you need to do this repeatedly in several rounds of restrictions. And this means that it's really, really hard to maintain the structure of your formula. It has to be like extremely robust to withstand such massive restrictions. Like pigeonhole principle is somewhat well behaved in this regard, in the sense that even if you map most pigeons to holes, you still have like a small pigeonhole principle left. I'm lying now because it's much more complicated than this, but at least you sort of have this property. Also for XOR constraints, you can make the argument that if you have a Satan formula, you can sort of remove most of the graph and you still have a smaller graph over which you have a Satan formula. But in general, this is not so easy. So we really need more tools for bounded depth Frege. In the other direction, you can extend Frege with the possibility to define variables that carry the meaning of a formula. Just define a new variable x that has the same truth value as a sub-formula. That's extended Frege, essentially. Substitution Frege is a Frege proof system where you can just recycle. You've done a nice subderivation. In a single step, you can say, oh, I want to recycle this subderivation, but apply it to other premises, and then clearly I should get this other consequence. So it's like recycling lemmas, if you will. These proof systems are believed to be exponentially stronger than Frege, both of them. They're known to be polynomial equivalent. And now we're obviously like way beyond anything we can prove lower bound for. One interesting thing, though, is that you could actually define extended Frege and substitution Frege for smaller proof systems. And then you can study how they relate. And we know that you can go all the way down to resolution, and you can define resolution with an extension rule. And that is, in fact, known to be polynomial equivalent to extended Frege. On the substitution side, it's not at all clear that this would be true. you can sort of, you need to think about it like what is substitution resolution and what is extended resolution. Are they the same or are they different? Probably different, but we don't know. The ideal proof system, and mostly by now I'm cheating you on all the definitions, but very roughly it's Nullstellensatz, except you can write your Nullstellensatz proof with your polynomials represented in any which way you like. And now you get a very, very powerful proof system. There are some conditional results that basically relate extended Frege and the ideal proof system and lower bounds. There are some unconditional results where you limit what type of arithmetic circuits you're allowed to use, where there have been papers by researchers like Nutan Limaya and Srikant Srinivasan, I think is very claimed to be the state of the art. Bounded arithmetic is one of these other things we're not even talking about. It's kind of a way to use logic to do computational complexity theory. You set up a theory of arithmetic, except that you're doing arithmetic with one arm tied behind your back, or maybe both, depending on exactly which model you're in. In particular, I think, I'm really not an expert on this, but you're allowed to do induction, but you're severely limited in the power of your inductive hypothesis. And exactly how you limit your power, that depends on, like, you get different type of theories in bounded arithmetic. The point is that different theorems, different theories will correspond to, they can be translated to proof systems, and bounded arithmetic gives kind of a uniform way of, if in bounded arithmetic I can reason about, say, a combinatorial principle, then that proof you can then sort of in a one-shot way translate into a whole family of proofs for the propositional encodings of the corresponding combinatorial principle. And there's like the, what is this? This is Paris-Wilkie translations and things like this. There's a pretty high threshold, I think it's fair to say, for someone from the outside, like I am, to bounded arithmetic. But it's worth thinking about if you're just getting into the area, like if this is something that is worth reading up on and learning, because it seems like it can be a powerful tool, and in particular some of the bounded Frege, the first breakthrough lower bounds for bounded Frege were discovered in bounded arithmetic. And then it was translated over to a language that didn't need bounded arithmetic any longer. But I think like the reason we have the lower bound in the first place, the original paper by Aitai, was that somehow bounded arithmetic was a powerful tool that helped to find this proof. Some techniques that we didn't talk about at all that would also be worth studying if you want to claim to know proof complexity. In particular, when you go up to Shirley-Adams and higher, duality plays a very important role. Where, for instance, if you're reasoning about LPs, that the optimal, say, minimal value for one LP will be the maximal value of the dual LP. And this means that you can work on both problems at the same time and sort of prove upper and lower bounds. And the same holds for sample squares. And this is somehow very useful. We talked about reductions. With low-depth decision trees and low-degree polynomials, that I think is a useful tool that hasn't been used so much. Switching lemmas I talked about, I think this is well worth studying. Razborov's pseudo-width technique, I think, is quite interesting, and it might be worth studying what is known about weak pigeonhole principal formulas and how such lower bounds are proven with pseudo-width. When we're looking for new techniques, there have been recent work over in circuit complexity where they try to do so-called top-down like proofs for lower bound size instead of, I mean, somehow switching lemmas are in some sense bottom-up proofs, I guess. This is mostly at the conceptual stage, I think, but this is something to be aware of, that people are working on developing new techniques for analyzing circuits that could quite potentially be interesting in proof complexity also. Interesting applications that it's maybe a little bit embarrassing that we didn't talk at all about total NP search problems, but we didn't. It's something that is well worth knowing, that the search problems in NP that are not sort of probably NP complete, because if you view them as decision problems, the answer is always yes. But the interesting problem is to find the witness. There's a rich collection of different such problems. And what has been discovered is that when you want to understand how these relate to each other, turns out that different classes of TFNP problems correspond in a fairly precise way to different proof systems. And this has led to quite exciting developments and arguably like a number of breakthroughs that you can ask about different total NP search problems, and then you can translate it into separation results for, say, Shirley-Adams and other things. For instance, this separation result that I talked about that separates resolution and Shirley-Adams with unary coefficients, I think is basically a TFNP. Okay, that has some consequence over there that I don't know off the top of my head. And it has also given rise, actually, then for some TFNP, there's a way of like, if you have a TFNP proof problem, then in some sense, via this correspondence, you do get a proof system one way or another. How natural these proof systems are sometimes open to discussion, but there's a quite intriguing two-way connection. I already talked about circuit complexity, that there are moral parallels, but proof complexity gets stuck earlier than circuit complexity. Recently, I think there's this interesting three-way connection between, which I think you saw also in the cutting planes lecture, some of them, where you're asking about proof complexity questions, you're asking about circuit complexity questions, and communication complexity and lifting theorem somehow answer all of these. And so there's a three-way feedback loop between communication, circuit, and proof complexity, which is quite interesting. Another thing that we didn't talk about at all, but it's important to know about, especially relevant for Shirley-Adams and sums of squares, is that these proof systems have been used to analyze the question of, for instance, suppose I want to solve an NP-complete problem, and I have an LP formulation, and I can ask, well, how well can I do if I just I lift it to a higher dimension and sort of add new constraints, and then my original problem would be a projected down version of this problem to the original space. And you can ask, like, can this help me to solve the problem more efficiently? You get to questions like extension complexity, and there have been results, very strong results that are in some sense basically proof complexity results. The final application I want to talk about is my favorite application, namely to use proof complexity, not to prove lower bound, but to prove upper bound for combinatorial solvers, for say SAT solving or integer linear programming or something else, where we have the problem that these problems are NP complete or NP hard. So the solvers, and there are amazing solvers that typically run in linear time, but they're highly optimized, and so oftentimes buggy. So how do we know when they're correct and when they're buggy? And the idea is that the standard solver would just take a problem and output an answer, like the optimal value of the objective under these constraints is 42. And now certified solving, or solvers with proof logging, the idea is that the solver should also generate like a proof in the proof complexity sense. So that after the solver has terminated execution, you take the input, the claimed answer, and you take the proof. And then you basically go over this propositional proof and check if the proof is valid or not. And if it is, then you should accept the answer. Okay. So if you want to use proof complexity in proof systems for proof logging, then what do you want? Well, on the one hand, you want ideally a super strong proof system because you want to make the solver's life easy to generate these proofs. But on the other hand, the whole point of having the solver generate the proof is that I mean, the original solver is like hugely complicated, and you know that it's buggy pretty much. And so you can't trust it. And so the reason why life would be better if you had the checker is that presumably you can trust the checker. But that means that the proof also has to be very simple. So you want an extremely powerful proof system, but that should be extremely simple to check. And then this becomes like an applied proof. And can we design, now you have all the ideas of proof complexity at your disposal. What would your proof system be? Can we design a proof system that is good for this task? Yes?
Yeah, maybe I'm missing something, but like, for example, if your checker is extended Frege, it seems to me like it's very powerful, right? Of course, but also checking that the derivations are correct is not that complicated. Or maybe I'm missing something?
No, you're going in the right direction. In general, yeah, no. So you'll end up with something like that. Extended Frege is, in general, though, I think it will both be too slow to check and too complicated to write such.
It's still too slow to check. Okay.
Too slow, okay. And also a little bit too complicated because, like, again, the way you can think about, like, suppose I want to do some symmetry reasoning argument or something, and like we don't even actually know if Frege can do that. Maybe it can, maybe it can't. Okay. But this is like, okay. But yeah, no, we'll yeah, exactly. It's something. I think you're headed in the right direction. In particular, one challenge, like why aren't the proof system we've looked at so far, why aren't they good enough? Because solvers will typically do without loss of generality reasoning. So a very important part will be to say that you add a constraint, and the terminology is terrible, but this is what it's called. The constraint is called redundant with respect to a formula f. If I can add it to the formula, and it doesn't change the satisfiability status of the formula. Like if the formula was unsatisfiable, then it's obviously still unsatisfiable. But if the formula was satisfiable, then I can safely add this constraint. Okay? Any constraint with this property is called redundant. So our proof systems will need to support addition of redundant constraints because these are all kinds of, if you have again, suppose you're in a purely symmetric case and you just split the tie somehow. Then you will add a constraint that splits the tie and you want to say this is without loss of generality. And resolution, cutting planes, polynomial calculus somehow inherently cannot do this because this is no longer implication of reason. But here's the way you can do this. You can have a very generic condition that says basically that C is redundant with respect to F if and only if, this is an if and only if, the following holds. You take F, and you take the negation of C, and there should be some kind of substitution, mapping variables to literals or truth values, such that F union the negation of C should imply F union C not negated, all of this under the restriction or the substitution omega. I claim that this is an if and only if. If I can find such an omega, then C is redundant. If C is redundant, then such an omega exists. Okay? And just this requires a proof, and I won't do it because it's getting late in the day, but let's just sketch the interesting direction. The interesting direction is, what are we nervous about? We're nervous about that there was a perfectly good truth value assignment alpha that satisfied F, but it violates C. Okay, so we had a good solution, but now you're adding a new constraint and that violates alpha, so this solution disappeared. And now I want to argue that's fine because there is another solution. Okay. So since alpha satisfies F but violates C, that means that actually alpha satisfies the premises. So it satisfies the conclusion. Okay, but now I just have to unpack what it means that alpha satisfies F union C under omega. That just means that the composition of alpha and omega satisfies everything. If you just unpack what this notation means. So the role of omega is to sort of give a patch that says that, well, you maybe don't need to patch alpha. Maybe alpha is still good, but if it isn't, then here's how to patch it. So it's a very like algorithmic notion. And now you can define you can make this into a proof rule, provided that we should be a little bit nervous because implication is not like semantic implication is not good. So we'll just turn this into like a standard derived symbol. Like if you want to do this, if you want to derive C, then you should actually give me proofs in your proof system where you derive all of these guys from this guy. Or maybe you could say that it's obvious. For instance, if all the constraints here are weakenings of the constraints in here, then we're also fine. Okay? So just to make sure we're on the same page, let's see how this would work. Suppose, for instance, here is like one thing that extended Frege would do. Suppose that A is a fresh variable. I want to define A to be true exactly when X and Y are both true. And suppose I'm doing Canonical planes, then I just want to add these two constraints. That 2 not A plus X plus Y greater or equal to 2. That says, well, if A is true, then X plus Y are obviously both true. And this constraint says that if A is false, then at least one of X and Y is false. And somehow I should be allowed to, if A is fresh and doesn't appear anywhere else, then this should be legible. And I claim that our rule will allow us to do this. And the question is only like, what is our omega? And our omega is exactly the reason we're using to argue that this is okay, that I can, A is free, so I can set it to be what it should be. So let me start by deriving 2 not A plus X plus Y greater or equal to 2. That's easy. My witness is just, I'll set alpha to false. And then this whole constraint vanishes. And since A was fresh, nothing happened to F. So clearly I can add the left constraint. Are we happy with this? Okay, now for the right constraint, again, A doesn't appear in F, so we're fine. And what should my witness be? Well, in the same way, the reason the right-hand side should be okay is that I can just fix A to true. And then that vanishes. Okay, but that now I have also this constraint to take care of. So I need to somehow derive under my witness that sets alpha to true, I should derive 2 not alpha plus X plus Y, meaning I now have a proof goal that I have to prove unconditionally, right, that X plus Y, X and Y are both true. Why is that true? Well, that's where not C comes in. Because as a premise, I have that apparently this is false. It is not the case that A plus not X plus not Y greater or equal 1. But that in particular implies that A is false and X is true and Y is true. So indeed, the premise actually implies, so the negation of this implies this under the witness. Okay? And this you can actually now make like fully algorithmic. It's going to be a little bit expensive to check, but importantly, like I have to give you the omega if I want to do this. But if I do, then this will be perfectly checkable, and like SAT proof system checkers like DRAT-trim will check this, and this very PB checker will also check this. This is in fact like the very PB format of this. Now, here are some interesting questions. Obviously, so this shows that in particular the extension rule in extended resolution is a special case of this so-called redundant space strengthening. So now we got a proof system that is at least as strong as extended Frege. And in fact, it's polynomial equivalent. But the interesting thing that we didn't have with the extension rule is if you look at this rule, that we're slowly getting back to, this makes perfect sense to define even if I don't have new variables. So suppose I allow you to use this rule, but you're not allowed to introduce new variables. Am I making sense? So it's an extended Frege without extensions. And now you can ask, what is the proof power of this proof system? And this we don't know, except that we know that the pigeonhole principle is now easy. Satan is easy if you just have resolution plus this rule. But but there are no new variables, so it's not obvious that we could not prove lower bounds. Okay, and suppose that you can do this. Here's another challenge, like another way of, suppose I allow you new variables, but I only allow you new variables to be equivalent to clauses that have already been defined. So somehow why extended Frege is so powerful is that you just throw out random definitions and then you build arbitrary circuits. But suppose I only allow you shorthand for a clause that you have already derived anyway. How powerful is that? That's like maybe seems like a little bit more powerful than this, or maybe incomparable, I'm not sure. Why do I care about this question? Well, because this is actually what SAT-based optimization solvers do, so-called max-SAT solvers. They use this rule heavily. So they actually do extended resolution, but only in this very limited set. And it seems to work really well. So these are two like applied questions. Yes?
And so this, and this is, I don't know exactly what substitution resolution or substitution Frege is, but like that's not substitution. The second rule that you're showing here.
No, this is I'm defining so that so this is just a shorthand for saying I have to tell you exactly what this is, but I'm just saying you're allowed to introduce a new clause Z, and then you just write down the clauses that force Z to true precisely when C is true.
And that is not equivalent to reusing computation. Reusing reasoning. That's why.
No,
okay,
but you can ask but you could ask, will this allow me to somehow simulate substitution proof systems, which is a slightly different question. But here, no, I'm just allowing you to introduce this as a definition. And this would be like, suppose C contains W literals, then this equivalence will be, if you think about the W plus 1 variables. Basically, you would say, if Z is true, you would get one clause that says not Z or C. That says that if C is true, then if Z is true, then C has to be true. And then you would get W clause that says that basically if Z is false, this forces every literal in the clause to false. So this would be like W binary clauses. So the proof rule just says, for a clause C that you've already derived, you can get these W plus 1 new clauses for a fresh variable Z. But only if C was already derived. How much does that buy you?
Okay.
Does the question make sense?
Yeah.
So, and then I just want to say that you can now also, suppose we're trying to solve a Siena formula and minimize some objective, which is over here, F. Then how should I change this strengthening rule? Well, omega is sort of telling me how to patch solutions. But if I'm minimizing an objective, then I want to make sure that the patch never makes my objective bigger. So then I would add this as a proof rule. So this is like the optimization version of the rule. And now something interesting happens. Suppose I can prove something stronger. Suppose that I have a witness omega that is so good that it actually strictly decreases F, which is now F is an integer linear form. Okay? So it strictly decreases F. Then I claim that it's actually sound to derive C if from the original formula F plus everything I've derived so far, plus the negation of what I can infer, I can prove that I'm driving down the objective strictly, plus I just reprove the original formula, but nothing else. Is the notation making sense? So I claim that it's valid to infer C if I only prove this. But note that I no longer have this proof goal and no longer have this proof goal. This making sense? So why is this sound even? So the interesting thing is, so for simplicity, suppose that we haven't derived anything. Suppose that this is the first rule. So I just have my input formula, and then I want to infer a new constraint. Okay? And suppose I prove this to you. Again, very explicitly, there is an omega, and I did derivations and everything. Now, suppose we have an alpha that satisfies F, but violates the new constraint. Well, then alpha composed with omega satisfies F and has a smaller objective. Yes? Okay, so now we're in one of two cases. Either it satisfies C and then we're happy. Otherwise, we're in this setting again. We have alpha composed with omega satisfies F but violates C. So I apply my rule again and I see that alpha composed with omega twice satisfies F and gives me a smaller objective. Okay? Now, either C is satisfied and then we're happy. or let's do it again. I'm getting a strictly smaller integer, non-negative. And you see that this, has to terminate. And so it has to terminate with some alpha composed with omega a number of times that only improve the objective and is satisfying my original formula and the new constraint. And note that this is nothing that we do, right? This is just something mentally happening inside our heads. We just proved this once. And then they said, because I've proven this, I'm allowed to infer C in a single shot. Is this making sense? Okay. And then you can even, okay, but I cheated you a bit. Suppose that now we're further into the derivation and we have derived more things. Well, then it's not so hard to actually just do nested induction to prove the same thing. Or you sort of, one way of thinking about it is to pick alpha to be the minimal assignment with respect to the objective that satisfies F union D, and then you just do a contradiction on U. And in fact, you can also define this in general. You don't need to have an objective. You can define it with respect to any preorder. And you could even, like if you think about it, you can switch preorders if you're a little bit careful, but I won't go into the details. The interesting thing is that now we have a proof system that, as was shown by Kolodješek and Tappen, is believed to be strictly stronger than extended Frege. This is G1. And now, why is this interesting? Well, this is interesting because you can say, I'm only interested in SAT. Okay, that's fine. But if I'm just solving a satisfiability problem, I could invent an objective. For instance, I can say, decide whether F is satisfiable and minimize the Lex order of the assignment. Right? Either F is unsat, and then I will be able to prove unsatisfiability, or else I find that lexicographically smallest assignment. But I didn't change the satisfiability status. But since I invent this objective in my head, I can now apply this dominance rule that it's called, which allows me to do fully general symmetry breaking. So this is, and then it turns out that I should do this based on top of not resolution, but cutting planes is somehow a much nicer base system. So it turns out that for large areas of combinatorial solving, for all we can tell today, you take the cutting planes proof system, you take this redundance-based strengthening rule, and then also the dominance rule, and now, surprisingly, you can formalize efficiently a lot of what combinatorial solvers are doing. But this also brings a problem, because, again, modern solvers will typically have symmetry handling. And symmetry handling has been getting much, much, much better. To the extent that a lot of the problems that we think of as hard now, like if you think about the pigeonhole principle, if you think about the clique coloring formula, like why are they hard? They're just hard because the proof systems have to reason about symmetry. But if I told you, if you had symmetric reasoning, you're solving the clique coloring formula, and I tell you, oh, without loss of generality, the clique is the first M vertices. Well, then it's obvious that the first M vertices are not M-1 color. And the problem we're having now, if we are trying to use proof complexity as a computational, like as a tool to study combinatorial solving, we have a lot of lower bounds for cutting planes, for polynomial calculus, for resolution, where the lower bounds are heavily using that the formulas are symmetric. And symmetric formulas aren't hard in practice. So, and the point is, but then you said, but not all our lower bounds were symmetric, right? Random KCNF is not symmetric. Average case coloring is not symmetric. So probably we're using something else. But the point is that it would be nice to formalize this. Like it would be super nice to be able to take, and I think this is where I ended the first lecture, to take resolution or polynomial calculus or cutting planes and somehow enhance it with some notion of saying, yeah, and also anytime you want to use symmetry, you can do this. The problem is how to define this. If you define it in a naive way, then you can obfuscate formulas so that they don't look symmetric. If you define it slightly too carelessly, then everything becomes, very, very hard to prove lower bound. But like for me, that I'm exploring the interface between theory and practice, this is like one of the most interesting problems, I think, that can we somehow, I love studying resolution polynomial calculus and cunning planes, and they're highly, highly algorithmically relevant, except can we somehow get a nice proof complexity theory where we're including symmetry awareness? Okay. So just to repeat that the two authoritative references for this, I guess, is the SET handbook, where the proof complexity service in chapter 7. Krajicik's book contains lots of goodies, also even more goodies on the advanced side. So what did we do in the end in this course? We ended up focusing squarely on combinatorial solving and proof systems that are used for that, resolution, corresponding to SAT solving, Nordström and polynomial calculus, corresponding to Gröbner basis, and cunning planes corresponding to pseudo-Boolean solving and maybe to some extent integer linear programming. We hoped to talk about Shreya-Adams. That didn't pan out, and sum of squares and stubbing planes we didn't really talk about. Now, in the very final lecture, we did talk a little bit about the extension rules. It turns out that what I showed you, it was kind of clear that it was stronger than extended resolution, and you need something like this even to model like the pre-processing that is being done in modern, say, SAT solvers or mixed integer programming solvers. But we didn't talk about Shreya-Adams, sum of squares, stubbing planes, extended resolution, and also, resolution over parities, Frege, the ideal proof system. So there's room for more courses as soon as you have recovered. The focus of the topics that we selected was, again, proof complexity as a computational lens, where actually the lower bounds that we prove for resolution for polynomial calculus, for cunning planes, are actually have a real impact in that they tell us things about algorithms that are being used on an everyday basis. And I think what we have seen in our research also is that we are actually building much, much, much better solvers thanks to the fact, for instance, that we understand cunning planes and polynomial calculus better. One example that I mentioned today, like the realization that, hey, dual variables actually makes polynomial calculus exponentially more powerful. And it was possible to turn this into a paper that improved state of the art in hardware verification. I think our enhanced understanding of cutting planes is what allows us to build a so-called pseudo-Boolean solver that is considered to be state of the art today. But we also get problems in return, right? We get, for instance, can we do proof complexity for different cut rules? And lots of other problems. I think space complexity, the whole area of studying space and studying time-space trade-offs are in some sense algorithmically motivated, but are really nice theory questions. So I think the main conclusion, what I hope to have, to some extent at least, demonstrated during these lectures is that you can do quite a lot of fun proof complexity just in this area of where theory and practice meet and I guess socialize with each other. So with that, it's my turn to thank you for sticking around till the end and taking this course, which is now officially over, at least the lectures. Thank you so much.